Well, thank you very much. It's really a pleasure to be here at the Isaac Newton Institute, and I'm very grateful to the organizers and to the Institute for having me here. We'll come back to this chess problem a bit later. I'm going to start at the beginning. Okay, so I'm going to talk about infinite chess and the made in n problem, and also the omega 1 of chess, what we call the omega 1 of chess. This is joint work with a number of co-authors. The first paper will appear as part of the CIE conference, and then there's a second paper which is still in preparation. The first one is available on my webpage. Okay, so infinite chess. What is infinite chess? It's chess played on an infinite board, an infinite edgeless board, like the integers z cross z. We use the regular pieces, and they move in the way that you would expect on an infinite board. And each player, of course, is striving to put the opposing king into checkmate. But unlike regular chess, there's no standard starting configuration. Instead, the way you play infinite chess is you first specify the opening position, and then you play from that position. So that's how a game starts. There's no standard starting configuration. Rather, part of the game is to specify the opening, the starting configuration. So let me clarify a few of the rules. For the most part, we insist that there's at most one king of each color. There's no boundary, so we don't have to worry about promoting pawns to queens. You can never reach the edge. There's no castling. There's no en passant rule for pawn capture. We abandon the 50 move rule in ordinary tournament chess. If there's 50 moves without a pawn movement or a capture, then the game is declared a draw. But I view this as a sort of approximation to the threefold repetition rule. It's just that when the pieces are just kind of moving around and no progress is being made, it's too hard to tell when the repetition has actually occurred, and this is the historical reason for the 50 move rule. So on an infinite board we get rid of this rule because the real draw rule is that infinitely long play counts as a draw. And for that reason we can get rid of the threefold repetition rule, because if someone wants to force a draw by repeating, then they could just play forever, so it amounts to the same thing. So because we're allowing arbitrary starting position, there's additional weird boundary cases that you have to think about and get the right answer to. For example, if it's white's turn and black is in check and white is in checkmate, then what is the outcome of the game? Does anyone have a view on that? Some people might say, well, white is in checkmate, so white is lost. But I say, no. Black is lost because it's white to move and black is in check. And so if you think about the real meaning of checkmate, it has to do with the necessary possibility of capturing the king. And so if it's white's turn and black is in checkmate, then white can actually take the black king on that move. It doesn't matter that white was in checkmate, which has to do with the possibility that black might take the white king on the next move, but that would be after white already captured the black king. So the right answer to this configuration is that white wins, even though white is in checkmate. So okay, there's these weird cases. Just for thoroughness, one has to come to an understanding. Let's see, my computer is not responding here. Okay, so the mate in n problem, in the genre of chess problems, mate in 2, black to mate in 3. My daughter, Hypatia, has a book of mate in 1 exercises that she's looking at. Okay, so this is the problem of determining whether you can force a checkmate in that many moves. So the mate in n problem is, given a finite position in infinite chess, can white or black force a win in at most n moves? So here's a mate in 12 problem that I put up earlier. So the question is, so this is a black king, and the other pieces are white. So can white force a checkmate in 12 moves or fewer? And I'm not going to tell you the answer right now, but I'll come back to it at the end. Okay, so the mate in n problem, as I said, the problem of determining whether a designated player can force a win. And the question from the computability perspective is this a computable question? Is it a computable problem to determine whether a given finite position is mate in n? And if you think about what it means to be, say, mate in 3, well, a position with white to move is mate in 3 if there is a move for white, so that no matter what black does, there's a white response, so that no matter what black does, there's a white move that delivers the checkmate. So in chess, when you say 3 moves, you count only the moves of one player, not both players. So basically, this is a very complicated arithmetic assertion with 5 alternating quantifiers. And there's no reason to think that such a kind of question should be computably decidable. It's not even CE. I mean, this is a sigma 5 assertion. Now, in finite chess, of course, one can search the entire game tree, and this is basically how the chess computers work. They look deeply into the game tree, and in principle, one can search the entire tree. And so on a finite board, of course, the optimal play is computable. But in infinite chess, the game tree is not only infinite, but it's infinitely branching, because in a given position, there are infinitely many possible moves. A bishop can go a little bit out or further, sort of arbitrary far. So the tree is infinitely branching, and one cannot expect to computably search that tree even to finite depth. Even if you only want to look 5 moves ahead, there's still infinitely many things to be looking at. You cannot search the game tree in principle. So the brute force solution doesn't seem to show anything about decidability. Now, there's various other decidability questions. For example, the winning position problem, can a player force a win from a given position? Or the mate in n problem, or the drawn position problem, can you force a draw from a given position? The stalemate position problem, can you force a stalemate? Draw in n is sort of an ambiguous phrase, because what does it really mean? If you are in a position so that you can force infinite play, then you're in a drawn position. But maybe the strategy itself is not computable, right? So one has to be careful. Stalemate, however, is a clear situation. I mean, stalemate means that a player has no legal move from that position, and that's something that's computably decidable, whether a position is in stalemate. And so the stalemate in n problem is the problem of determining, can you force a stalemate position in at most n moves? There's a kind of approximation to what you might mean by draw in n, which is draw in n by k-fold repetition. So in other words, given a finite position, you want to ask the question, can one of the players force in at most n moves, force the position into a set of k positions such that that position is forcibly closed under play. So can one player force the game to stay inside this set of size k? That would obviously force a draw. So it's an approximation to what you might mean by draw in n. If you formalize each of these problems directly, you get statements with very high arithmetical complexity and many alternations of quantifier with little reason to think that they should be decidable. Okay. Now, even though a position might allow infinitely many legal moves, it seems, if you think about it, that there seems to be a kind of equivalence for sufficiently distant moves. And you can get an idea about that. For example, if you have a finite position and it happens that there's a bishop move that makes checkmate because maybe it's moving out of the way or something, or maybe it's protecting another piece, then if it was a distant move that delivered checkmate by a bishop, then any sufficiently distant move by that bishop in the same direction will deliver checkmate. And so somehow it didn't matter. It was sort of like you move the bishop to infinity, and that's what's delivering checkmate. It didn't matter how far away you went. And so there's a kind of pseudo-infinite branching to the game tree. It's really only finite branching. Okay, now if you push that kind of reasoning further, then you can start to understand what's happening after 2 and 3 moves. And Corey Evans and I realized that sort of the mate in 2 problem is actually decidable because of this kind of reasoning. Mate in 3, okay, it's much more difficult to understand what's going on. And as we went a little bit higher, well, 3 is as high as we got with that kind of reasoning, we felt that we had to understand sort of all of chess in order to make the argument go through. And so I became a little bit discouraged about carrying it out. But the fact that even though the natural formulation of these assertions is sigma 6 or something, the fact that that was decidable strongly suggested to me that, in fact, the mate in n problem should be decidable, and that's what we conjectured. And then later on we proved it. So the mate in n problem is decidable, even though that natural formulation is 2n alternating quantifiers. Furthermore, there's a computable strategy for optimal play for both sides from a mate in n position. So if the position is made in n, then the winner can achieve the checkmate in the quickest possible way by computable play, and similarly the loser can delay the checkmate as long as possible. Furthermore, from any position, if it's possible to avoid checkmate for k moves, then there's a computable strategy that does so. And similarly for the stalemate in n and draw in n by k. So we get, in all of these cases, computable strategies.
Are those strategies uniform in k?
Yes. Yeah, and n. So the decidability problem is uniform in n and uniform in the position. Okay, so to prove the theorem, we introduce what we call the first order structure of chess. So it's a first order model structure. The objects, the domain of the model consists of all of the finite chess positions. So we represent them in some particular way. So what is a chess position? Well, it's a finite list of the pieces and their locations and their types and their color. And maybe you also have a bag of captured pieces, finitely many already captured pieces, and also an indicator for whose turn it is. So a position is sort of a complete description of what you need to start playing from that position. And then we put some relations on this structure, namely the relation that says you can move from this position to that position with one legal move, by the person whose turn it is to play. And a relation indicating whether a position is white is in check or white is made, and then so on for black also. So all of the kind of obvious basic concepts of chess that you would want to refer to, we put into this structure of chess. If we have a given list, a given finite list of piece types, then you can reduct the structure. I guess it's a submodel, not a reduct, to the positions using only those pieces. So the made in n problem is expressible in the theory of this structure. I'm not saying that implies it's decidable yet, but the made in n problem with those alternating quantifiers is expressible in this language as an assertion in this structure. And now the key lemma of the proof, of the decidability proof, is that this structure is automatic. It's an automatic structure in the sense of finite automata theory, which means that it can be represented as a set of strings, and the relations can be represented as relations on finite strings, such that the strings form a regular language, meaning that it's the set of strings accepted by a finite state automata. So an equivalent way to understand what is a what is a regular language is that it's the set of strings that are recognizable by a read-only Turing machine with, say, a fixed number of tapes. Now, it's a general fact that any automatic structure has a decidable theory, and the way that fact is proved is by means of the pumping lemma idea, which basically reduces these infinite searches. The difficulty of deciding the theory of a structure is that you have an existential quantifier and you don't have time to sort of try out all the possibilities, but because of the pumping lemma, in a regular language, if there is a witness, the question about whether there's a witness or not, it boils down to a finite search through the pumping bound, the pumping length. And so one can tell, so one can reduce those infinitary searches to finitary searches. And this idea is really just the same as this idea that we were reasoning about with the bishop and this sort of equivalence relation on this set of distance moves. Yes?
So what kind of chess piece types do you include? Because
just regular chess piece types.
No, so it's for real chess. It's not like a fantasy chess where you have some.
Right, real chess pieces. Yeah.
Bishops.
Kings, queens, rooks, bishops, knights, pawns.
So you allow sort of other kind of.
No. Oh, so for A, it might be you can have 200 black bishops and 16 white bishops, and right. So okay. So I'm sorry. These are just ordinary chess piece types, but the question is how many black rooks there are and how many white pawns there are, and so on. So one of the key.
Surely this is just an example of something more general about the kinds of pieces. It can't be specific to chess.
This theorem is not specific to chess.
No, of course not.
Yes. Okay, but on the next slide I'm going to discuss what is it about chess that made it automatic. Okay, I'm not going to give all the details because there isn't enough time. It's in the paper. But you can also do the same proof with Pressburger arithmetic. Instead of thinking about automatic structures, maybe you just like to think about Pressburger arithmetic, which is maybe better known in some circles. So this is the structure of Pressburger arithmetic. You have the natural numbers with only addition. Of course, you can define the order from that. So not only is the structure of chess automatic, but it's definable for a fixed list of piece types. It's definable inside this structure. And the reason it works, this is the fact about chess, to answer your question, is that queens, rooks, and knights move on horizontal lines, vertical lines, and diagonals. And those kinds of lines are definable in Pressburger arithmetic. This is the key fact that makes the structure of chess automatic. If the movement of the pieces, if the movement of the distance pieces was following, parabolas or something, it wouldn't work at all because you can't define the square function in Pressburger arithmetic. And you wouldn't get regular language if somehow you needed multiplication. But you don't need any multiplication for chess. It's really about addition because of the nature of the lines of movement. This is really the key fact about the ordinary chess pieces, is that they move on very simple lines, and even though they're infinite, you can represent them in Pressburger arithmetic. And therefore, since Pressburger arithmetic admits elimination of quantifiers and is a decidable theory, you can decide the maiden end problem and the stalemate end problem and so on by asking a certain question about whether a certain assertion is true in Pressburger arithmetic, and that is a decidable question.
You're saying these pieces move in line, so bishop.
Yeah, bishop moves on a diagonal, right?
And rooks move horizontally, vertically. Does this work if you allow some sort of special bishop that can move sort of 2 across, 1 up, or 4 across, 2 up?
As long as you can
6 across,
represent
3
it
up.
definably in Pressburger arithmetic, then the same proof would work. But if you had a bishop, say, that moved on a diagonal, but the number of steps had to be a prime number, it couldn't move anywhere on the diagonal, it can only go, on a prime number, then it wouldn't work because the class of primes is not definable in Pressburger arithmetic.
What if you allowed concatenation of lines? So say you allowed a knight to move some finite number of knight steps rather than just 1 knight step.
Oh, if it was an arbitrary number.
Arbitrary number, so maybe 2 across, 1 up, and then what? Yeah, so sort of zigzags.
Well, then it could go anywhere. So then I think it would work again. Because that rule allows the knight to go anywhere. Well, no, other pieces are in the way. Okay, let's see. I take that back. I'd have to think about it. I mean, that arbitrary many moves is not something that's expressible directly, but if you said up to 10 moves or something with a fixed bound, then you would be able to express it.
Is the fact about automatic structures stronger because you get infinitary results for automatic structures? It's not just that it's just not just that it's decidable, but actually they're infinitary statements which are decidable.
I see.
Automatic
So,
structures.
I see. I haven't thought enough about that, but that might help me out actually with some other questions I have. So I want to talk to you more about that afterwards. So, because I'm not quite clear on that. You mean in some infinitary logic, you still get the decidability?
Absolutely.
Okay, I definitely want to talk to you more about that. Let's see what's going on here. Okay, so I want to emphasize that the one position problem is still open. We solved the maiden end problem, but that's not the same as the winning position problem, right? So the winning position problem is, given a finite position, does white have a winning strategy from this position to force checkmate in some finite number of moves? Now, it could be that white has a winning strategy, but it's not maiden end for any particular n, because there are finite positions in chess that have the property that white is going to win in the sense that there's a winning strategy that white can follow, but black can force a delay as long as he wants. He can't force an infinite play because that would be a draw, but he can say, well, this time it's going to take you 1,000,000 moves to beat me. And then they play the game again from the same position, and black can say, this time it's going to take you 1,000,000,000,000 moves to beat. He can announce any n and say, okay, you're going to beat me, I concede that, but I'm going to make you take n moves this time, right? So such a position is said to be value omega. Okay, so the question asked by Richard Stanley is whether this is decidable, and we don't know the answer. It's still open. It's what's called math overflow hard, meaning that it was asked on math overflow and did not get an answer there. Okay, so these are the value omega positions. It's not even clear whether the one position problem is hyperarithmetic. This is not clear. It's sigma 1, 1, of course, because you're asking, is there a strategy which is an infinite object? Okay. Let me consider the question about computable play. So does insisting that the players play according to a computable procedure affect our judgment of the outcome of the game? So a position is computable if there's a computable function telling you where the pieces are and how many there are of each type and so on. There's some complications with this idea of a computable position because, for example, you would maybe want it to be computable, the question of whether a given square is attacked by any piece. And for a finite position, of course, this would be computable if you knew where all the pieces were. But if you have some infinite position and you know how many pieces you have of each type and you know where they are, it doesn't mean that you can tell if, say, the king is in check, because you know there's infinitely many queens and you can go and find more and more of them, but you don't know if one of them is on the same file as the king, so you don't actually know if that square is attacked. Okay, so there's some issues about that. What is a strategy? Well, it's a rule for playing given the initial configuration and given the finitely many moves that have been made so far, and a computable strategy is just such a rule that's given by a computable function. So the question that interested me is, can requiring the players to play according to a computable procedure affect whether or not we regard that position as won or drawn? And the answer is yes. So requiring the players to play according to a computable procedure can affect the answer. So there's a position in infinite chess. It's an infinite position. It has infinitely many pieces. It's a computable position. It's drawn, so neither player can force a win. But if you insist that the players play computably, then the position is a win for white, because white has a computable strategy which defeats any computable strategy by black. It doesn't defeat the incomputable strategies by black, so black has a non-computable strategy to force a draw, but white can beat all the computable strategies by black. And this is the position. So, okay, so you fix a computable tree with no computable branch, which is an easy exercise in elementary computability theory, the existence of such trees. And then you make a copy of that tree in the plane. So there's mostly rooks here. All the pieces are white except for the black king. All the pieces are white. I don't know, it's sort of hard to tell the color. There's a black king right there, a white king. There's rooks everywhere. And then there's bishops lining these channels. And the channels should look just like the tree. So there's periodically branch points here. And at a terminal node of the tree, there's this pawn configuration that happens. So how does it work? Now, the idea is that white is going to force black through the tree. So it's black's turn. He's got only one move. He's got to move up the tree, and then white comes behind, and then black has to move again. If he's at a branch point, he gets to choose which way to go. If he chooses to continue this way, then white comes behind, and black keeps marching up the tree. So white is like has a whip, and is forcing black up the tree. And because of the principle of Zugzwang, which is the principle that there's no other move, black has to go up the tree. If he's playing according to a computable procedure, then black cannot find the branch, because there is no computable branch in this tree. Therefore, black will eventually find himself in one of these dead ends. And what happens in the dead end? Well, white forces him in to the dead end, black takes the pawn, white comes behind, black moves to the very end, and then white checkmates with the pawn. So, yes?
So this tree, at each vertex has two edges coming out, one of which is a dead end, the other which...
No, not at all, not at all. No, it has whole big finite parts that ultimately are dead ends.
In that case...
It's a binary branching tree with no...
Run into itself?
If it was like that, it would have a computable path, because you could avoid the dead ends by just looking ahead a little bit. So this tree has the property that there's big... What's that?
It's a puzzle one class. So
Right.
Isn't this thing going to run into itself? I mean, you're now bounded by the actual size of the board, right?
No, I hope it's clear that the tree fits. I mean, I put it... no, because you can fit the whole... In fact, I have another picture in the paper. You can fit the whole binary branching tree, a copy of the whole binary branching tree with all of the branches in the plane, if you think about it. If you try to draw it, you'll figure it out. You can fit the whole tree, 2 to the less than omega, in the plane, and this is just a piece of it. So, yeah, I can show you a picture later. So, yeah, it definitely fits.
Okay.
What?
the whole tree.
The whole tree, yes. Okay, but it's a problem because we can't fit omega to the less than omega in the plane, which is related to this final part of my talk. But I think I'm going to run out of time. How much time do I have? Oh my gosh. Okay. So, all right. Okay. So there's alternative versions of that configuration. You can fill in the channels with pawns, and you're forced this way. White makes checking moves with the pawns instead of pushing the black king with the white king. Every move is check now. And there's a So there's a further simplified version. Now it's all pawns except the rooks here are organized like the tree. And if you think about it, this piece here is not protected by anybody. So black can take that piece, and then the pawn can come from behind with check. And so the black king ends up capturing pawns following this tree. It's just a slightly simpler formulation. It's easier to deal with because none of the pieces can move, and it's easier to sort of prove that it's doing what you want. There's a symmetric version. So this is the same as the other position, and this is the same one with the opposite colors upside down. And it has the property that it's drawn, but the first player has a computable strategy to defeat any computable play by the opposing player. So whoever goes first gets to work on their part of the board and have it. So it's just like the other one, except it's you can say who goes first and still get with the same position. Okay, so I'm not going to have time to cover everything, but there's this concept of game value in chess, and I already mentioned the value omega positions are the well, if you have what's called an open game, this is a game which is won after finitely many moves, then it comes along with this game value concept. It's a way of assigning ordinal values to the positions. It's a generalization, really, of the maiden n idea. So a maiden n position has value n, but more generally, a position has value alpha plus 1 if white can play to a position with value alpha, and if it's black's turn, then the ordinal value is the supremum of the ordinal values of the positions to which black can play. So value omega means that black can announce a lower bound on the length of the game at the outset. Value omega plus 10 means that white can force to such a position in at most 10 moves. Value omega squared means that black can announce the number of announcements he will make, such that at each announcement it's the number of moves that will be made before the next announcement, and then after the final announcement is up, he might lose. Okay, the omega 1 of chess is the supremum of the ordinal values of the finite positions, and we don't know the value of this ordinal. It's some countable ordinal. The best lower bounds that we have at the moment are omega times n plus k. Corey Evans and I have some candidate positions that we think have value omega squared, but nothing is definite yet. Andreas Blas and independently Philip Welch observed that the omega 1 of chess is at most the supremum of the computable ordinals. Let's go now to the infinite position case. And so I just want to show you a few of these positions. This one is called releasing the hordes with value omega squared. Okay, all the pieces are white except for 2 black rooks and a black king. And this pawn right here is the portcullis, the door. We have to open the door to get the queens out, and then we can checkmate the black king. So the way it works is this rook is about to be taken, and if that rook is taken, then this bishop can get out of the way, and that pawn can move up, and this pawn can move up, and the door will be open. So we have to get these pawns out of the way so that we can open the door. But the rook doesn't want to be taken right away, so instead the black rook goes up very, very far as he wants. The pattern continues above, right? These pawns continue. So the black rook goes up, and then it's captured by a white pawn. So if the rook is here, then this pawn can capture it. And then white's strategy is to move these pawns out of the way, and eventually this pawn gets moved out of the way, and then the bishop comes out, and then this pawn, and the door is open, and the queens come through. So the idea, though, is that, okay, the rook goes up, is captured, but then before white can start moving these pawns, black says, no, 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 check with his black rook. So white says, I'm in check. What does white have to do? He can't just run away, because then black can just check, check, check forever, and it will be a draw. So white has to do something about this check. So he has to move towards the black rook. Okay, and then black checks again, come towards, check again, and so on. And then eventually, the white king and the black rook are right next to each other, so black can't check anymore, so he moves 1,000,000 miles away. And then white says, aha, I've got a free chance. And he moves 1 pawn. And then black says, check again. And then it's check, 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 1,000,000 moves. Okay, and then black has to move away again, 1,000,000,000,000 moves. And then white says, aha, I can move another pawn. Okay, and so on. So every time you move a pawn, black gets, 1,000,000,000,000 additional movements of delay, just the stupid checking of the king. And this makes it value omega squared. So the number of announcements he gets to make is the height he moves the black rook up, and each time he moves his black rook away a certain distance, that's the number of plays that will occur before the next announcement is made. After all, the doors open and out. Then this is what we call a lock and key position. It's a similar thing, except now you can't start it because the rook is not under attack. This is the key. If white takes this pawn, the key is released. The white pawn comes up, attacks this pawn, and black doesn't take, but rather allows white to take, and then the black rook. It's a lock, and white has the key, and then, okay, so combining it with other configurations, now you can iterate lock and key structures to get omega squared times n plus k. We have successive locks and keys to get through with n of them. You can combine these together to make positions with value omega cubed. You have one long branching point. It goes into separate apartments. Each apartment has omega squared times n plus k. So the value of the overall position is omega cubed. We conjecture that the omega 1 of infinite positions in infinite chess is true omega 1. And we had a proof idea, but it didn't work in two-dimensional infinite chess. But we were able to make the argument work in 3D chess, which is a much older concept than you think. It was first defined in 1907. Not infinite 3D chess, but just finite 3D chess. He started with 8 by 8 by 8, but then went to 5 by 5 by 5. And it's featured in many episodes of Star Trek. So the theorem is that the omega 1 of three-dimensional infinite chess with infinite positions is true omega 1. And the basic proof method is to look at the well-founded trees, subtrees of omega less than omega. There's a connection between playing on those trees and the rank of those trees as a well-founded partial order. And so we need to embed such trees into positions in a similar way to what I described already. But we can't quite fit it in 2 dimensions, but we can in 3. So let me stop there. Thank you very much.
Thank you very much. So we had lots of questions in the talk, and things are running a bit late, so maybe we can move on to the next speaker, if he's around.